Some people call it the most brilliant idea in modern physics, maybe even our best shot at a theory of everything. But to others, well, they'd call it a total failure, a dead-end fantasy that's not even wrong. Today, we're diving into the massive intellectual war over string theory, a battle for the future of physics itself.
So, has it failed? For decades, this one question has literally split the world of theoretical physics in two, with some of the smartest people on the planet on opposite sides. And look, this is way more than just a squabble over some equations. This is a huge conflict about what science is and where it's supposed to go from here. To really get what this fight is all about, we've got to rewind back to the 1970s. And you have to understand, this was an amazing time to be a physicist. They'd just put the finishing touches on the Standard Model, this incredible theory that described pretty much every fundamental force, except for one big one, gravity. So the next step seemed obvious, right? Find one single theory to unite it all.
And that's where this wild idea enters the picture. What if the most basic building blocks of our universe weren't little points, but were actually these unimaginably tiny vibrating loops of string? It's a beautiful concept. Think of it like a violin string. The way it vibrates gives you a specific musical note. Well, in string theory, the way one of these little strings vibrates determines if it's an electron, or a photon, or a quark. It's this incredibly elegant way to get this whole zoo of particles from just one fundamental thing.
Now, this idea started out kind of on the fringes, but then, in 1984, boom, a series of breakthroughs, what they called the first string theory revolution, solved some huge mathematical problems. All of a sudden, string theory wasn't some niche curiosity anymore. It was the main event. By the 2000s, it completely dominated the field. But after all those years, the doubts started getting louder and louder.
Yeah, the honeymoon period was definitely over. A serious scientific backlash started picking up steam, and it was led by some really big-name physicists who were basically saying the whole string theory project had gone off the rails. And then, in 2006, the whole thing just blew up into the open. Two bombshell books came out, The Trouble with Physics by Lee Smolin and Not Even Wrong by Peter Waite. And their message was absolutely devastating. They said, look, after decades of work and tons of money and resources, string theory hasn't made a single testable prediction. Not one. And worse, it's choking out any other new ideas. So that kicked off this huge, messy, passionate debate that's been raging ever since, in blogs, articles, and conferences. And it really all comes down to three big sticking points: the problem with predictions, the question of evidence, and whether the math itself is even rigorous. All right, first up, and this is the big one, the prediction problem. The number one charge from the critics is that string theory just doesn't make any unique predictions that you could actually go out and test. And a theory that can't be tested, well, they say that's not really science, is it? So why is it so hard to test? It all comes down to a single, mind-blowing number. This number right here, that's the Planck length. It's the scale where the strings themselves and all their weird extra dimensions would supposedly become visible. To say that this number is small is probably the biggest understatement you could ever make. It's incomprehensibly tiny.
Okay, try to wrap your head around this. Imagine you could somehow blow up a single atom to be the size of a coffee cup. Got it? To see something at the Planck length, you would then have to magnify that coffee cup another trillion times. So yeah, seeing it directly isn't just hard. It's completely impossible with any technology we can even dream of.
So, what do you do with a scale like that? Well, the critics, people like Voigt and Smolin, say the problem is way deeper. It's not just that it's small, it's that we don't even have a final, complete version of the theory to make predictions from. But the defenders, like the physicist Joe Polchinski, they push back. They say the scale is the real issue and that we just need to be smarter and look for indirect evidence, just like the early scientists did when they first started thinking about atoms.
And that leads us right into the second big clash, the evidence question. If you can't see the strings directly, are there any other clues hiding out there that might tell us we're on the right path?
Defenders will point to a couple of really intriguing hints. First, string theory seems to allow for a huge number of possible universes, a landscape they call it. And that makes it seem more likely that a universe like ours, with this tiny specific amount of dark energy, could exist. Second, some of the really complex math from string theory has, kind of out of nowhere, been super useful in describing the weird plasma they create in particle colliders. But the critics, they are not buying it. They say these are just mathematical coincidences and that the dark energy argument is a philosophical cop-out. And finally, we get to this really nasty argument about the theory's foundations. Is the math even solid?
Is this thing even built on a firm footing?
So this is a pretty brutal charge. Voigt's book is called Not Even Wrong for a reason. He's saying the math is so incomplete and ill-defined that it's not even at a point where you could prove it wrong. But defenders like Polchinski shoot back that, hey, physics isn't pure mathematics. You make progress with the tools you have. And they point to these powerful new ideas called dualities that show how different-looking versions of the theory are actually the same thing in disguise. For them, that's the rigor the critics are missing.
Okay, so you see this intense back and forth over the technical stuff, and it kind of raises a deeper, more human question about how science actually gets done.
You have to ask yourself, right, if the critics are right, if this thing has failed so badly, then why are thousands of the world's most brilliant scientists still dedicating their entire careers to it? What's really going on here?
While you get two totally different stories. Smolin and Voigt, they basically accuse the whole field of groupthink. They say string theory has such a monopoly on university jobs and grant money that it's almost impossible for any competing ideas to even get a chance. But the defenders say, no, that's just what collective scientific judgment looks like. The best and brightest are flowing into string theory because it's still the most powerful, most promising path we have.
Ultimately, this whole fight pushes us to ask a really fundamental question about science itself, especially when we're trying to study things that are way, way beyond what we can see or touch. Like, what does the word evidence even mean when you get to these frontiers?
This entire debate is a perfect example of this deep idea from the philosophy of science called theory-laden observation. It sounds complicated, but it's actually pretty simple. It just means there's no such thing as pure raw data. Every single thing we observe, every piece of evidence we collect, is already being filtered and interpreted through the lens of our existing ideas and beliefs.
The philosopher of science Heather Longino said it so well. This naive fantasy that data are just pure facts directly speaking to us, that's just not how it works. And that idea is right at the heart of the string theory wars.
So at the end of the day, this isn't just a debate about tiny vibrating strings. It's a debate about what we even count as scientific evidence when direct proof is totally off the table. When does a cool mathematical trick become a real clue about the universe? When does a surprising calculation point to a deeper reality? The string theory wars are like a high-stakes masterclass in how scientists try to find their way in the dark.
And that leaves us with the biggest question of all, not just for physicists, but for anyone who's curious about the edge of what we can know. When our best tools, observation and experiment, just can't help us anymore, how does science possibly move forward?